Hey, this is Josh from Leet Dev, where we explain programming questions as simple and concise as we can. Today we're going to talk about a famous problem, the N-Queens. N-Queens is a popular question that a lot of people use in reference to recursive backtracking. Today, we'll look at how we can solve it using recursive backtracking, along with how we can use some slight optimization with caching with dales and hills to help speed up our algorithm. Given the input n representing n-queens, we want to form a n by n chessboard such that no queens can attack each other, and we want to return all distinct solutions to the n-queen puzzle. Specifically, our output, we want to have this matrix of dots and q's, where q represents the queen and dots represent nothing. Looking at example 1, we can form two chess pieces, and we'll just look at one of them. For those who are not familiar, in chess, a queen piece can move in 4 directions. They can move horizontally, vertically, and diagonally. What we want to do is we want to place queen pieces in such a way that they cannot attack each other. So in our second example, this queen does not touch any of the other queen. In our third example, this queen also does not attach any other queens. And also in our fourth queen, also doesn't attack any other queens. And as you notice, as I drew out these lines, no other color touches the queen except for the color that originated from them, which gives us a valid answer. The problem wants us to generate every possible combination of queen layouts where they don't attack each other. Whenever we hear a problem like this, it usually means we have to do some sort of recursive backtracking algorithm where we try every single possible combination. An idea to start is, let's just start with picking a row and then picking a random column where we want to put our queen in. So row 0, we decide to put our queen in column 0. Now let's try our next combination. In row 1, let's put our queen on column 0. This won't work because it would be under attack by our first queen. So maybe we try the next column over at column 1. We would face the exact same problem because this queen would be able to diagonally reach our queen. And so we try column 2. At this point, that queen is safe and we can try our next row. On row 2, we can try column 0, but that would be in danger. So we can try column 1, also in danger, and it's pretty much in danger in every single move. So that won't work and there's no valid solution. So what we could do is we go back to row 1, and then instead of picking column 2, we can try column 3. And then advancing forward on row 2 again, we can see that we can place a queen on column 1, row 2. Now this pattern basically repeats, and we just try every single possible combination of queen placement until we have a valid answer. To more formalize our problem, whenever we have a recursive backtracking algorithm, we need to define a couple of things. The first thing is we need to define our recursive state. In this instance, that will be our row. For every row we're in, we want to pick a column to try and place our queen. Next, we have our base case and our recursive case. Our base case is when we know we've reached the end and we have a solution. Our base case for the n-queen problem is when our row is the same as our n, meaning we have placed all the queens, and all we need to do at that point is generate our answer and store it in our list. The magic of this algorithm comes in from our recursive case, where we try to place every queen in every column. So let's say over here, the first thing we would do is we would see if the current column that we picked is valid or not. So in row 1, column 1, we know that's not valid because it can be diagonally attacked by the other queen. So we try another one and we see that column 2 is safe. And because column 2 is safe, we decide to place the queen and then we recurse to the next row. When we are done recursing whether we found an answer or not, we would come back to row 1 and then try recursing again with a different column value. The runtime of this algorithm is O of n to the power of n. And that's because we have n queens, and for each of the queen that we have to check and make sure that it is valid, which can become computationally expensive. The spacetime of this algorithm would be O of n squared, because at the end of the day, our algorithm wants us to recreate this board, so it'll be n squared. For some interviews, that might be enough. However, we can actually optimize this problem slightly. One problem is that notice that to check if our column is valid, we have to do an extensive search. We have to check all the rows, all the columns, and all the diagonals. If we can somehow cache these values of the queen, we can actually make this linear lookup a constant time operation, helping us speed up our algorithm. We can further optimize this problem by caching the row, columns, and the diagonals that we would set when we place the queen. So we don't need to worry about rows, because whenever we insert a queen, we would recursively traverse to the next row. So by the fact of doing that, it's already guaranteed that our row will not have any duplicates. However, what we need to keep track of is our column. For example, let's say we place a queen here. We can set a Boolean true on index 1 of our array over here, and then whenever we place the second queen on column 1, we can quickly look up our array to see if we have placed the value or not, instead of having to linearly scan our vertical values to see if the queen has been placed or not. Now, what's interesting is trying to detect diagonals. To clarify them, we have hills, which are the vertical diagonals. The interesting part about diagonals is that if you were to add the column and rows together of any grid that's diagonal to each other, they actually equal the same. For example, over here, well, let's say our queen, 1 plus 1 is 2. One of the diagonal at row 0, column 2, it's 0 plus 2, which is also 2. And so all these values are the same. And so if we can store these diagonal values based off of our location, we can do a quick lookup to see if our queen is diagonally attacked by another queen. So the range of values for our array is from our smallest value, which is 0 plus 0, 0, to our greatest value, which is 3 plus 3, which is 6. A quick way we can create the size of our array is to use 2n. Our n in this example is size 4, so that'd be 2 times 4 equals 8. And this would give us an array of 0 to 7, which would give us just enough space for us to store our hill diagonals. Now, the dales, which as I believe is basically low flatland, which I guess is why it is a downward diagonal. Downward diagonals actually have similar properties. For example, if we do row minus columns, they will always be the same. So in this instance, we have 0 minus 0 is 0, 1 minus 1 is 0, 2 minus 2 is 0. However, we will have a problem with the range of our dales. For example, let's say we have a column of 3 and a row of 0. That'd be 0 minus 3, which will give us negative 3. We can't have an array of negative 3, so we need to somehow compensate for that. I will quickly formalize this. Our range would be from negative 3 to 0, 3 minus 0, which is 3. So we still have that same length of our array, which is 2n. We just have to deal with the fact that we have some negative numbers. And we can quickly solve this by just taking the value that we have, which is row minus column, and then just add our n minus 1. And this will help offset our negative number so that negative 3 plus n minus 1, which is 4 minus 1, will give us 0. And now this will offset all our values so that our lowest value would be at index 0. And then we would still have our array of 0 to 7. And so by using this optimization, we can do a constant time lookup to see if we can place our queen or not, instead of having to manually iterate through all the rows, columns, and diagonals. As a result of doing this, we now change our algorithm to be O of n factorial, because now we can just do n lookup times n minus 1 lookup times n minus 2, and so on and so forth, which results in n factorial. Spacetime is still O of n squared because while yes, we are adding extra arrays now with linear time arrays to store value, we still need to generate our output string, which is of size n squared because we need a n by n answer. Buckle your seatbelts because this one's going to be a doozy. First, we're going to define all of our Boolean state variables. They're only used so that we can quickly reference them instead of having to pass down everything. It's mostly just a style decision. One thing that we didn't really talk about is we have this array of integer called queens. This integer will represent all the columns that we've taken for a specific row. So while we do know that we have taken a specific column, we don't know what column is associated with what row. And so when we want to generate our answer later on, we can quickly look up our array of queens to see what column we picked for what specific row. And we can get more into that later. Now that we defined everything, let's set up our helper function to do our recursion. As always, with full recursion problem, we need to set up our base case, which is when our row is equal to n, and our recursive case. We'll define the add solution function later. In our else case, we have picked our row. We now need to pick a column and see if we can place it. As mentioned before, in our recursive case, we have 4 things we need to do. First, we want to make sure if our row and column is not under attack by another queen, and we define a helper function to check this later. And if it's not under attack, we can place the queen, and this would require us to set all the variables that we have on the left side. And then we call our helper function to recurse to the next row where we would pick another column to place the queen in. And then finally, whether or not we found an answer or not, we need to remove everything we set earlier so that it doesn't mess up our input when we try another column. This is it for the recursive function. Now we just need to define all of our helper functions. In our isTaken function, we just do a quick check in all of our caches to see if we have placed a queen previously in any of our columns, our hills, or our dales. We've defined our place queen and remove queen function. What we did here is for the queen, for the row that we are currently navigating in, we set the column that we placed. This will come in handy later when we generate our solution. And then we set the specific index for our column, our dale diagonal, and our hill diagonal to be true. And we do the very same thing in remove queen, except we set them to be false. The one thing we didn't need to change is the queen array, and that's because we will be overriding it anyways when we place the next queen. And now the final part of this is we need to define our helper function add solution, which would generate the list of Q's and dots that represent our matrix. So what we did here is first, remember our output is a list of n list items that contains dots to represent empty spaces and Q to represent the queen. What we did is we took the column that we set for our queen at each row, and then we iterate through everything from 0 to n. And when our j is equal to the column value that we set, we add Q to our string. Otherwise, we just append a dot to represent that we didn't put the queen. Once we iterate through our first row, we would store the generated string from our string builder helper into our list. And then once we finish iterating through all of our rows, we add our list into our answer, and then we continue trying to backtrack and come up with a solution. Now I won't go through the full example because recursive backtracking problems can be huge. Let's just start off with this. So we start off at row 0. Row 0, we enter our helper function. We didn't hit our base case, so we enter our recursive case. We pick our first column, which is column 0, and we go and check if our queen is under attack, if we replace it there. Right now everything is false, so is taken would return false, and the opposite of false is true, so we enter a recursive case. When we place our queen, we set the column 0 to be true. We set our hill, which is 0 plus 0, to be true. And then we set our Dale, which is our row minus a column plus a 3, essentially. So 0 minus 0 plus 3 is 3. So we set 3 to be true in our Dales. Next, we recurse to our next row. So on row 2, we try column 0. We see that we have a conflict when we try and test to see if it's under attack, because columns inside our column array, column 0 is true. So we know that this will return false. And so we'll try moving our second queen to be column 1. We'll check again to see if it's taken or not. Since we're at column 1 now, we don't hit anything in our 1 place. However, we will hit a conflict for our Dale. Specifically, 1 minus 1 is 0, plus 3 is 3, and we see that 3 is already in our list. So that's a no-go. So we move again and try our next. I won't do the math every single time, but there's no conflict. And so we add the column 2 to be true, and we add our hill 1 plus 2, 3 to be true. And then we also add 1 minus 2 is -1, plus 3 is 2. So we set 2 to be true. And then we recurse and try another example. Let's just say we already know just from looking at the example multiple times that it doesn't work and we didn't hit anything. So what happens here then is, let's say we go back to row 1, we recurse back, and now we finish our helper function, and now we have to remove our queen. So what we do at this point is we set all the previous values that we set to be false. So in this specific instance, at row 1, column 2, we would essentially remove column 2. Our hill, which is 1 plus 2 equals 3, is now false. In our Dale, which is 1 minus 2 plus 3, which is 2, is also false. So we set them to be false. And then we would try again and move our queen to the next column. And so I'm going to skip ahead and just get to the point where we actually reach an answer. Now let's say we've found one of our answers and we're now at row equals 4. We hit our base case and we call our add solution function. What we do inside our add solution function, so we're iterating through each of our rows. I didn't draw it in the array, but we can look at our map over here and we can figure out what column we picked for each row. So we just pretend a little bit. We're going to pick a string builder, and the string builder is basically just a char array, so to speak, so we can create a string without causing extra runtime complexities. It's a Java thing. And then we need to generate our string. So since n is 4, we need to build a string of size n to represent our answer. In row 0, we know that 2 is where we set the column. So what we do is we iterate through our array, and then we set 0 because our j value is not the same as our column. 0 again for j1, and then at j2 it would be the same as our column. So we put a queen, and then we put another dot at j3. Now we have our first list, and we add that into we add our first string into our answer list. And then we just kind of repeat building up the strings that we have. And then at the very end of all of this, we just add our generated list into our answer list. And then we just backtrack and continue until we've explored every combination in this problem. And then finally, we exit our helper function, and then we just return our answer, and that's it. Now let's submit our answer, and yes, this should be a string, not a... All right, submit our answer. And there you go. And this is how we would solve the N-Queen problem. In most cases, maybe just doing a naive horizontal, vertical, and diagonal scan might be enough to solve this problem. But if you want to further optimize, you should remember the interesting math properties of looking for diagonal numbers. Now, if you have any questions, please leave them in the comments below. Otherwise, if you found this video helpful, consider maybe liking this video and subscribing to get daily updates. Otherwise, I'll catch you in the next video. Have a beautiful day.